Hey class, all right, time for example 3, last one. And for our grand finale here, we are going to compute the length of one arch of the cycloid. Of course, the cycloid keeps going on forever. You could say it has infinite length, but if we just narrow our focus to one of those humps, it is something we could do for sure. And as you saw last time, it's a good idea to get sort of a feel for what kind of answer we should be expecting. So if you remember when we graphed the cycloid, it had kind of a look like this to it. This was 0, and this was 2 pi r. And as far as about what the length of this should be, well, I mean, the length of this, the horizontal line segment there is 2 pi r. So since we are going not just horizontally by 2 pi r, but we're also kind of going up and then back down, we would expect a bigger length than 2 pi r. So this should be greater than 2 pi r. That's supposed to be a greater than 2 pi r, and as we know, pi is about 3.14, so we're expecting certainly something bigger than 6.28 r for this. Of course, that's just a rough estimate. What we'd like to do is get this exact, and so let's get to it. Well, we know that we're going to need to have our derivatives of our parametric equations here. Now, if you remember, there it goes again. We had x equals r times theta minus sine theta. And then the other one was for y, that was r times 1 minus cosine theta. Now, if you think, that looks a little different than what we did in class, a bit. I factored the r's out, and it makes it look a little different, but it's of course the same thing other than that. Maybe just be a little more convenient to keep track of everything this way. Okay, so then differentiating for our dx over dt, well, again, the r is a constant multiple. That just factors out. You know, really here, I should say dx over d theta, because theta is what we use as our parameter typically for the cycloid. So our derivative then is going to be r times 1 minus cosine theta. Okay, so not bad there. And then dy over d theta. Similarly, r is a constant multiple that we can pull out. This time, the 1 is just going to go away and differentiate to 0. And in fact, the minus sign is also going to go away, because when we differentiate cosine, we get a negative from that will cancel with the negative that we already had. And so we end up with just r sine theta for our dy over d theta. Okay, so let's look at our arc length formula now. So length, it's going to be the integral from 0 to 2 pi, because that's how the range of theta is for one hump of the cycloid. And then we've got square root here of our the sum of our derivatives squared. Now, when we square dx over dt, we're going to get, or dx over d theta in this case, we'll get r squared, of course, and then 1 minus cosine theta, that thing squared. And then we got to square our other derivative as well. Once again, we'll get r squared. Nice common factor there, as might be expected. And then derivative of sine, we got cosine. Oh, wait, that was already differentiated. So now we just have to square it. So we get sine squared theta. And then we'll have a d theta out here, like so. All right, well, we got the common factor of r, so let's go ahead and pull that out. It's positive, so its square root will just be itself. And in fact, we could go ahead and pull it all the way out of the integral. That's supposed to be a square root. Okay, so with the r's gone, let's see what's left. If we FOIL out 1 minus cosine theta, we'll have 1 minus 2 cosine theta plus cosine squared theta. And then from our other derivative, what's left there is sine squared theta, and look at there. Once again, cosine squared theta plus sine squared theta, helping to simplify things down a lot. We know that that's just going to be 1. And we had already had another 1 over on the other side there. So we can combine those and get 2. Of course, we don't want to forget we had a d theta out here as well. Okay, so we'll end up with r times the integral from 0 to 2 pi of square root of 2 minus 2 cosine theta. We got a d theta in there. Okay, and you may be thinking, well, hey, that integral does not look too bad. It's simplifying down kind of nicely, kind of right according to plan, and it should be an easy integral. But one thing that we do get here that we didn't see as much with the others is that square root stays here. And there's really not a substitution here where we could just let the inside be our new variable u. So we're going to have to be a little sneakier with this one. And what we can do for that is get a trigonometric identity involved. Okay, so let's take a look at what we can do. One trigonometric identity, which hopefully rings a bell at least slightly, is that sine squared x you can rewrite as 1 minus cosine 2x over 2. Okay, that might be a typical way that trig identity is phrased. Now, of course, in our case, we have theta, and we do not have that 2 in there inside the cosine for our situation. So what we'll do is we'll just adjust and let theta be 2x. That will now get us closer into the situation at hand. So we then end up with 2 sine. I multiplied the 2 from the denominator over to the other side. 2 sine squared of 2 theta. So theta over 2, right? Because there we're replacing x. X is theta over 2. Okay, and then that is going to equal 1 minus cosine theta. And if you use a slight amount of imagination, that is pretty close to what we have up there in our integrand. Because yes, there's some 2's there, but that's also a common factor. So we could go ahead and pull that out right away too. We got our r out here. Come on. There's r. 0 to 2 pi. We can pull that 2 out. It's just going to become a square root of 2. And then what's left in the square root is 1 minus cosine theta. Okay, d theta. And using our trig identity now, let's see. R, let's pull the square root of 2 out all the way. Integral 0 to 2 pi. Now, under the square root, we have 2 sine squared theta over 2. And, my goodness, that's a 2. Okay, and then d theta. And hey, now we've got the square, well, almost the square root of something squared. So once we get that kind of officially clear here, then we can go ahead and take the square root. Now we do have integral from 0 to 2 pi. Sign is negative on parts of that. So that does pose a bit of a conundrum, perhaps. Oh, but you know what? Good news here. So our argument inside the sign in this case is theta over 2. Yes, theta is ranging from 0 to 2 pi, but theta over 2, that then is going to range between 0 and pi. Yay, problem resolved, because we know on that interval sine theta over 2 is going to be greater than or equal to 0. Okay, so no nasty absolute values popping up in this situation. So we can go ahead and leave our integral as it was. Okay, and then square root of 2 we can split off again, just like we did before. Square root of sine squared, we now know that is going to be just sine theta, or sine theta over 2, thanks to our interval. And now we have something that we can integrate. Sine theta over 2, it's going to call for a little bit of a substitution, but nothing out of control. So let's go ahead and do that without writing a lot of the details out. So if I pull my square root of 2 out and combine it with the other square root of 2, I'm just going to have 2. Okay, and this time I'm going to keep my limits of integration, 0 to 2 pi. And I'm just going to anti-differentiate sine of theta over 2 directly. Antiderivative of sine is negative cosine. Okay, theta over 2. And then what we have to do is divide by the derivative of the inside, which is 1/2. So we divide by 1/2. I'm sure you can imagine that's going to correlate with multiplying by 2. We'll do that next step. We still got our d theta out there. Okay, so if we flip that 1/2 up into the numerator, multiply by the reciprocal, it becomes 2. We can pull that out again. And so we've got 4 pi sitting out front here. Okay, and then what's left? Oh, let's pull out the minus sign as well right away. And then we've just got the integral from 0 to 2 pi of cosine theta over 2. Oh, this is not an integral anymore because we already anti-differentiated. Duh. I'll do it like that. Let's see. We already had anti-differentiated on the previous step as well, didn't we? Grr. Okay, so this would be like so. 0 and the 2 pi. Hopefully you caught that quicker than I did. Okay, this is going to be 0 to 2 pi over here now. Okay, and then, okay, we flipped our 1/2. And this was not a pi, this was an r. Okay, minus sign is out there as it should be, cosine theta over 2, and still evaluating at 0 and 2 pi. Okay, now we can really go ahead and do that evaluation. Let's see, we better put it down here. And when we do that, we'll have negative 4r. And then we put in 2 pi. The 2's cancel. We got that 2 in the denominator, remember? So we've got cosine pi. And then evaluating at 0, we just get cosine of 0. And as long as you remember your basic values of cosine, you're home free here pretty much. So we have negative 4r, and cosine pi is negative 1. Cosine 0 is 1. Negative 1 minus negative 1, that is negative 2. Negative 2 times negative 4 is positive 8. And we still have our r in there, of course, so we end up with arc length of 8r. Okay. Yay! We now know the length of one arch of the cycloid. It's kind of interesting. You might expect it to be some nasty irrational number or something like that, but no, well, it's just 8 times whatever r happened to be. Comparing back up here to our underestimate. Our underestimate was about 6.28 R, and so we would expect something moderately larger than that, and that's what we got. We got 8 R there, so it turned out nicely. Another interesting way to think about this is, remember, we created the cycloid by rolling this circle. The circle had radius r, and so the length of the cycloid turns out to be exactly 8 times the radius of the circle that was rolled. Pretty cool. Hope you like that grand finale. That's our last example on computing arc length for the moment. So do make sure to do those practice problems, and remember hand in homework 6. Have a great weekend, and we'll see you again on Tuesday.